we have a great pleasure and honor to have today as a speaker Professor Jan Sloan from University of New Wales, and he will talk about pros and cons of lattice point sets for high-dimensional approximation. And please do not forget that after the talk we have some kind of virtual coffee break or like some time to chat with each other. So please.
Okay, so shall I start? Thank you, Tatiana, for your introduction, and thank you for staying up so late, those of you in Europe. And I don't know, we have some from Australia. I don't know if we have any from Asia, getting up early. But I want to talk to you about something that's not about sphere problems, as Ed and I have often discussed, but rather about a problem I think is very interesting, high-dimensional approximation. So let me begin. So the question is how to approximate a function of many variables, S variables, when S is very large. Of course, you'll face the famous curse of dimensionality. So if you think about the problem of approximation, well, I've written down a function f is approximated by fn. I'm talking about linear approximation. So in general, in most cases, it just uses point information of the function and some other functions of the variable y. So you need, first of all, you need a set of points at which to compute the n function values. And in this talk, they're going to be lattice points, but you need also, more than that, you need a finite dimensional function space for the approximation and a setting in which to set your exact functions. And you need a way of approximating, of constructing, you need an algorithm for constructing the approximating function fn. Well, I should just begin by saying that there is a tremendous amount of interest these days in high-dimensional approximation, and I've included just some buzzwords without telling you what they mean. But so polynomial chaos was invented by Norbert Wiener, generalized by Kaniadakis and Chu and others, generalized polynomial chaos. Reduced order modeling is a big thing in Europe, perhaps, especially Albert Cohen, Rendezvous, Wolfgang Dahmen, and others. It's sparse approximation and other nonlinear methods. Sparse approximation, which you have many zeros, you rely on having, most coefficients are zero. And uncertainty quantification. There are now at least 2 journals devoted to uncertainty quantification. And we do a lot of work with Francis and Alec, who are also on this call, in that space nowadays. So I'm going to assume that the function f is periodic in each variable. So we're working on the torus in the mathematical sense, functions that are defined on the torus and somewhat smooth. And we're very interested in methods that are both mathematically well-founded and efficient. So we're interested in solving practical problems in high dimensions, but we want to have mathematical guarantees that they work, which asks a lot. And so in this periodic setting, I used to think that there are almost no examples. Well, no, there are applications, but I will come to that later. So the approximation. So we're going to talk about linear approximation, and concretely, we're going to use kernel methods. Kernels, I will tell you about these things, of course. I don't expect you to know, but our kernels, in the end, we will have piecewise polynomial approximations. And the point set might be lattice points or something else, but I will talk mainly about lattice points. And the main reference is a recent paper published with Vesa Kanoya, Yoshihito Kazashi, Francis Ikuo, Fabio Nobile, fast approximation of kernel-based methods, lattice point interpolation and application. So it just appeared just in the last few months. So what is a kernel approximation? So a kernel approximation, suppose we're given, in this case, periodic function defined on 0, 1 to the s, a set of points in the half-open unit cube. a kernel approximation takes this form just as a linear combination of kernels with some coefficients yet to be explained. The coefficients ak, of course, depend on the function. And what is a kernel? Well, a kernel is a symmetric function that's positive definite. That is, if for every choice of points, yk, y1 up to y capital N, for every E capital N, and every choice of coefficients, that bilinear sum is non-negative and with equality only if bk equals 0 for all k. So I'm talking strict positive definiteness. So here in our case, a kernel approximation is an interpolant, which just means that our approximation is a linear combination, yes, of kernels, but you see, with one leg fixed at tk, at our points tk, and the other one is free, and coefficients now the interpolation property that fn equals f at each point in each of our chosen points. And so what does that do? Well, it's immediately clear that the coefficients are given by this linear system in which the matrix is k of tk prime. So the matrix determining ak is, of course, symmetric, and it's positive definite. And because of that, one always has a solution. So it has a unique solution because k is positive definite. It may be a very ill-conditioned system, by the way, but at least it's good to know that you always have a unique solution. The matrix is typically dense, so that can be a major cost. Well, in our case, just why we like the periodic setting, I suppose. The periodic setting is a simplification. We want our kernel to be periodic in this setting, naturally enough, periodic with respect to both variables. And we also want this sort of shift invariance property, which is not essential, I suppose, in periodic setting. But if you think about approximation on the torus, then you're certainly thinking that there is no special point, no special zero, if you like. So we have this shift invariance property. If we shift both variables by W, the kernel is unchanged. That's natural requirement. Well, then how are we going to choose the points and how to choose the kernel? Well, first about choosing the points. There are real advantages, the pros and cons, the for and against. The pros in choosing the points, the real advantage in choosing the points to belong to a lattice. Well, perhaps more technically, a rank 1 lattice. And so this is what they mean by a lattice. So let me just be sure that we are clear that tk, the kth point, for k running from 1 up to n, is a multiple of some integer vector z, an integer vector divided by n. So there's an endpoint lattice, and the braces around the side mean that you replace each component by its fractional part, because all this is invented by number theorists half a century ago. So Z, not only integer, but in fact, of course, because this is now modular arithmetic, modular n, in effect, so we can take Z between, well, 0 and n minus 1, but there's no point taking Z as 0 in any component. That doesn't help. So let's restrict ourselves to each component of Z lies between 1 and n minus 1. And how to choose the Z? Well, that's a big question. There are good choices and bad choices, but let me just be clear that we understand what a lattice method is. So this is now just in 2 dimensions. It's 34 points, 34-point lattice. Z, my integer vector, is 121. And so what does that do? Well, tk is kz on n. So starting with k equals 1, well, that's the point there. It's can you see my cursor, by the way? Is it visible?
Yes, we can see the cursor. Yes.
It just disappeared, but yeah. So at that point is 1 on 34, 21 on 34. That point there, that's k is 1. K is 2 will be twice it is up there, but now you take the fractional part to bring yourself back in the cube, and so K is 2 is there, K is 3 is here, and so on. And K is N would take you up there, but brings you back to the origin. So looking at that, by the way, that's a good lattice. There are bad lattices. You can take Zs to be all ones, then you just get all points on the main diagonal, which is by every test a bad lattice. And this one, I will mention just quickly, the 2134 are no accident in this sense that they are consecutive Fibonacci numbers. So this is a classical good lattice. And the good news is that Fibonacci lattices using consecutive Fibonacci points are good. The bad news is that that construction only works in 2 dimensions. There are no known good constructions in higher dimensions, but there are algorithms for finding good lattices. Okay, that we will come to. Right? Because all you have to do to find a good lattice is to find a good Z. You can go through and look at them all, but in hundreds of dimensions, it's hard to look at them all. So because the points form a lattice, the matrix elements simplify. And so we have there's a shift invariance property, but if K is K minus K prime Z and N 0. So the point is there are only N distinct elements in this N by N matrix. And moreover, each row is the same. Each column is the same, just shifted along by 1. It's what is called a circulant matrix. And circulant matrices have this magical property that they are easy to invert by fast Fourier transform. And so you need only N log N flops, which means that it doesn't matter how dense the matrix is, and the matrices are typically dense, kernel matrix is typically dense. And I did want to particularly say that this is not a new idea. The strategy advocated by Kernel and colleagues a long time ago, but it doesn't seem to ever come into any particular use. So how to choose the kernel? Well, we like to take the point of view that the function lies in some Hilbert space. I will come to say more about Hilbert space. It's a Hilbert space of periodic functions on the unit cube, or if you like, period of functions on the torus, S-dimensional torus. We like to choose K as the reproducing kernel of H. And excuse me while I move your images. And the reproducing kernel of H. And so that means to say that, well, if you don't know about reproducing kernels, they're very useful in numerical analysis. K of each with one leg fixed at Y as a function of the other variable is in H. And it's a symmetric function. It in particular has this this reproducing property, which is which makes the magic work. That the inner product of any function in F with the kernel, remember the kernel itself is in F, the H inner product reproduces the value at Y, at the kernel value Y, for all F in H for all Y. And from our point of view, well, there are many advantages to it, but kernel approximation has an optimal property which leads to an error bound. So this in some ways is well known, and of course kernels and reproducing kernels and what do I say? Radial basis functions based on kernels and so on are very much used on all manifolds. So this is the minimal norm property. If H is a reproducing kernel with kernel reproducing kernel K, sorry, if H, let me start again. If H is a reproducing kernel Hilbert space with kernel K, the kernel interpolant at a given set of points has the smallest H norm of any function in H that interpolates F at those points. And if you just allow me just for a moment just to yeah, sorry. Went the wrong way. Where did I go? What did I do? I'm sure you'll forgive me anyhow.
I think you went backwards in the slides.
Yeah, but I'm going forwards now. Yes. Am I going forward? No. What did I do here? Let me come back to my. Sorry about that. So, okay, so I just give the simple proof of the minimal norm because it's sort of, it's interesting. It gives really the point of all this, that f minus fn in a product with any kernel fixed at the point tk, one of the points tk, by the reproducing kernel property. The first term is f of tk, second term of fn at tk. Interpolation now gives us 0. So the orthogonal projection is actually the same as interpolation, or the other way around, right? It's they're the same thing, and that leads us to that means we have a Pythagoras theorem, if you like, that in the H norm, the square of f minus fn plus the square of fn H norm is the square of f H norm squared. That's because there's no middle term because fn minus fn is orthogonal to fn. And this makes it sort of so easy to work with that one has these beautiful Euclidean properties. So suppose that Gn, the minimal norm property, suppose Gn is any other function in H that interpolates f at the same points, then Gn minus Fn in a product with Fn, well, it's the same argument. This is just orthogonal, it's just interpolation, and we've assumed that they interpolate at the same point, so it's 0, and that then gives us Pythagoras theorem, and that gives us that Gn is greater than Fn. So the minimal norm property. In turn, that tells us that the kernel interpolant is optimal. So we are very interested in error bounds and so on. So the kernel interpolant is optimal in the sense of giving the smallest worst case error among all algorithms that use only those values of f at the same points, t1 up to tn. Well, the worst case L2 error by definition is simply the biggest error in the L2 sense for any algorithm. For the worst case error for a given algorithm is the worst case error for any function of unit norm, lies in the unit ball. And it's something that we make a tremendous amount of use of, this simple consequence that we want error bounds, right? So for any algorithm A, the L2 norm of f minus AF is bounded by the worst case error times the norm of f. It's just a simple scaling argument of the norm. But I mean, that's tremendously useful in the following sense. If you can compute analytically and then numerically, I mean, if you can actually compute the worst case error, then you're on the way to an error bound, and you can compute the worst case error from reproducing kernel Hilbert space arguments. And then you need to know the norm in the function space f. Anyhow, we'll make more use of that in the coming time. So the optimal property of kernel interpolation is that if AN star is the kernel interpolant, the one I've just defined, and AN is any other algorithm that uses information only at the same points, then the kernel interpolant is the smallest one, and it's a simple argument. I just give the linear argument here, but f minus fn is the same as f minus fn minus the an, because an times f minus fn is 0, since this algorithm an uses information only at the points t, where n has the same value. So so we get very straightforwardly by just so the function, the L2 norm is less than or equal to the worst case error times the f minus f norm h norm. Okay, so to get an upper bound, we can now go. I'll just tell you how we get an upper bound. We use this property that we have the optimal. Okay, so if we have any other approximation, and I'm just here going to use a trigonometric polynomial approximation, any other approximation that lives in the same space, then we get an upper bound. So this is, if you look at the second line, the second dot point, Fy is the Fourier series representation of F. Algorithm approximates this in two ways. It doesn't sum over infinite number of H's, just a specified finite set, a well-chosen finite set, and replaces the integral by a lattice rule, a lattice integration, a lattice approximation. So there are two sources of error, but the big thing that this kind of approximation has been analyzed extensively by Francis and others. Excuse me, and in particular, it gives us now expression for the worst case error bounded by this interpolatory approximation, the trigonometric polynomial approximation, which itself has a known upper bound. And that's the principle we use to choose Z vector. You've got to have some way of choosing Z. You can't just use intuition. You need some principle. We choose it to make as small as possible. And what choice of Hilbert space do we use? Well, for alpha and even integer, we use an unanchored but weighted Sobolev space of dominating mixed smoothness order alpha on 2. So you have alpha on 2 mixed derivatives we may say with respect to each variable. So the specific expression is the sum over all subsets. Those of you who do computation should be extremely worried about that because it's a lot of subsets. But anyhow, that's okay. This is just theory at the moment. The one on phi u is a weight. I'll come back to weights. The inner integral, well, you differentiate. Let's say, first of all, you differentiate with respect to all of the variables that are in the subset U. Differentiate alpha on 2 times with respect to each of those. And we then integrate over all the other variables. And wait, I've lost something here. Yeah, okay. And okay, so phi u is a weight. So says the subspace U, subset U. Sorry, that's a typo. Subset U. YU denotes the components of Y that belongs to the subset U, and Y minus U denotes the other components. And why do we choose this particular space? Because it has a beautiful reproducing kernel, which is known to us. So this is sort of very important. There are equivalent spaces, but equivalent norms, but you need a norm that has a beautiful reproducing kernel. So for those of you who are coming from number theory, I just say that for alpha on 2 functions in H, well, they have one mixed derivative. You can differentiate once with respect to each variable. So it's a space of dominating mixed smoothness of order 1, and they have all those functions have bounded variation in the sense of Hardy and Krause, with the usual setting for discrepancy-based bounds. So not surprising space in that sense. I do need to say something about weights because they may not be known to this audience. That weights in the function space setting have played an important role, I guess, for the last 3 decades or so, and are almost essential when S is truly large. Because small weight in that sense, phi u for the subset U corresponds to the subset U being of small importance. Because remember, the weight phi u occurs in the denominator. If the weight is small, then for the function to be in the unit ball, the derivatives have to be small. So subset U of small importance means small weight, and we really do need weights. The original weights starting 25, 30 years ago were all called product weights. Product weights take this form that for a subset U of the integers of 1 up to S, they're just a product of some numbers gamma j, positive numbers gamma j, but that doesn't quite sort of tell you. The gammas have to, in some sense, to decay. A classical result, I quote from numerical integration, is that the worst case error for integration is bounded independently of S if and only if, in a similar space, if and only if the sum of the gamma j's is finite. And that means, of course, that they have to decay faster than you may say gamma j is 1 on j won't work, gamma j is 1 on j squared will work. And so these are sort of well-known properties that you essentially need to have decay, or else the problem is too hard. And in some sense, all variables are equally important, and typically you really can't make much progress. But anyhow, now we have enough, we put those things together, we have enough ingredients to obtain a rigorous error bound. And so here it is. So for the worst case error, for an arbitrary lambda between 1 and alpha and 1, the worst case error is bounded by some unimportant number kappa on n to the 1 on 4 lambda times this expression here in parentheses. I know it looks a bit complicated. This is done by, well, first of all, you can write down, and because we're reproducing kernel Hilbert space, the worst case error is actually available analytically. And so, but then how do you find a good Z? How do you know what's a good Z? Well, we use this averaging argument. This expression uses a certain average over all Z. And then this lovely argument, I think, is just sort of so useful that there's always one choice that's as good as average. So you know that if you minimize that, then if you actually minimize this right-hand side, you will get a good Z. I'm sorry it sort of looks so complicated. You know, the awful thing is we have to have an arbitrary lambda in here. The best lambda is the smallest lambda. Good lambda is the small one. Lambda is 1 on alpha because that gives you 1 on n to the alpha on 4. Ideal choice is lambda is 1 on alpha, but now you see in this sum here we have the zeta function of alpha lambda. So alpha lambda must be smaller than 1. Must be smaller than 1. So hence we have a somewhat more complicated expression. And so I just simplified this. We state the bound more simply as the worst case error is bounded by some constant d depending on s, alpha, delta, and lambda into alpha on 4 minus delta for arbitrary delta goes to 0. And as delta goes to 0, the rate gets better, but the constant, the numerator, blows up. And now we can get an error bound, the L2 error. The L2 error is bounded by the worst case error times the norm, the H norm of F. So to go further, we need to, there we were. To go further, we need, of course, to estimate the norm of F, and that depends on the problem. So we should choose the weights. So this is now our point of view, that we choose the weights to minimize the product of D times F. The rate of convergence doesn't depend on the weights, but that means that we should always think about finding error bounds that depend on the problem. Well, it depends on the setting through the worst case error, but it depends on the problem through the norm of F. And so we need to come to a problem, and I'll do that in a moment. But let me now put together the pros and cons of lattice points. So the first thing I perhaps should have said when just writing down the formula for lattice points is they're extremely easily constructed, which in high dimensions, 100 dimensions, think of hundreds of dimensions, and n in the millions perhaps, it's very easy to construct, much easier to construct than all the points of a uniform array, rectangular array. So the second, as I've said before, the kernel matrix, though dense, is circulant. That makes it extremely easy to solve the linear system. Third, we have a rigorous error bound of this form with a known constant. So we really do have an error bound if we have a bound on the norm of F. And finally, the implementation is feasible and sometimes cheap enough, even for S in the hundreds, of dimensions in the hundreds, and N in the 1,000 or even millions. But we come, the cons. Well, the most striking con is that the rate of convergence that we have proved, n to the minus alpha on 4, is not optimal. The optimal convergence rate is n to the minus alpha on 2. Remember, alpha on 2 is the number of derivatives, so that makes sense in our mixed derivative setting. Now, moreover, we know that the rate cannot be improved. with lattice points, the order of convergence cannot be better than n to the minus alpha on 4 due to, I think, remarkable result from Byron-Hyde, Kammerer, Ulrich, and Vollmer. Tight error bounds for rank 1 lattice sampling and spaces of hybrid mixed smoothness. So that's a decisive con. You know, you can hope you can get methods that will have a better rate of convergence, but that are harder to implement. So towards implementation. So, well, first of all, you can't implement this until you know the kernel, since after all, we're using kernel interpolation. So the space H is a reproducing our particular space H with a very simple expression for the reproducing kernel. Well, it's the sum over all subsets of 1 up to S times gamma u. Gamma u is just a reweighting of their phi, so it doesn't matter, there's known constants. But times the product of all j and u of one variable kernels, eta, and eta is a trigonometric sum like this. And some of you will know trigonometric sum is just one variable thing, sum, of course, on h to the alpha. And if alpha is even, these functions are known in closed form. They are, in fact, Bernoulli polynomials. So the details don't matter, but eta alpha is b alpha of y minus y primed fractional part. So, of course, that makes it periodic. B alpha is a Bernoulli polynomial of degree alpha, and these are well-known, available B2, B4 polynomial of degree 4. And so the kernel interpolant is piecewise polynomial, in fact. And at last, I think we see the nature of Fn. It's only just become clear to me what is the nature of Fn in the end. So on cubes of length 1 on n, you can obviously divide up our unit cube into n to the s cubes of length 1 on n. I mean, just a regular partition. On each such small cube, Fn is a polynomial. As a function of yj for a particular j, it is, for alpha is 2, it's a C0 continuous piecewise quadratic. If alpha is 4, it's a C1 piecewise quartic, and so on. And so it's sort of useful to understand that's what we're actually getting. But can we in fact compute the kernel? Computing the kernel is in general not feasible because it involves the sum over 2 to the s subsets of 1 up to s. So it's not feasible, but for product weights, it is feasible and easy. Product weights take the form, so now my gamma, my weights in our gamma u, they're just products of gamma j's, and k is then, but you can easily see that this in fact is just a product of 1 plus gamma j of the eta alphas. To prove this, to check this, you only need to think about expanding out this product here. So 1 plus this gamma j. So you finish up, when you do that, when you multiply it all out, you get the sum over all subsets of the products of gamma j's over j in the subset. You see that works out? So it's actually very easy. And product weights, the method is fast. So the product weights, the method can compute the approximation at m arbitrary points in time of order. Well, you need to find your function values at n points. It's time sub t is the time for single evaluation. A linear system, remember, n log n. The number of m for m kernel evaluations. For each kernel evaluation, you take Sn in the product, because there is in the product, and that's a good way of doing it. Okay, and then there's an offline cost I won't worry about too much, but for computing the z's. For product weights, the method is fast, and that is something we are very interested in. And so I want now in the remaining time just to talk quickly about application. So in the world of uncertainty quantification, this is now very much a studied sort of problem in which it's a simple second order elliptic PDE minus the gradient of AXY, grad U XY equals G of X. Okay, so with Dirichlet boundary conditions, and the Y's here, well, in a standard model, live in minus a half, 1/2 to the power, and to the infinite number of them, perhaps, because the A is this sum mean plus a sum over yj's, psi j's, and rep unknown, given perhaps from the Calhoun and Loew expansion kind of expansion. And the y's are parameters representing independent random variables uniformly distributed on minus a half, each uniformly distributed on minus a half, 1/2. Perhaps I just say just a word about the model. So this kind of model is very commonly used in hydrology, underwater flow. So U here is the pressure, underground water flow. D, I should have said D is 2 or 3 dimensions. It's just, this is the physical domain. X, there are 2 variables here, X and Y. X is in the physical domain. Y represents random, Y are random variables. And so the AXY in there with this sum over these random variables, YJ, over all these things, the AXY is a field in the sense of, in the physical space, the X variable, but an uncertain field. It's a random field in the hydrology thing, representing random permeability, for instance, for oil underground flow. So we want to change the problem. We decided that problem, yes, it's okay, but you can get a more easily solved problem by making a small change here. So instead of yj, as we just had in here, we now have 1/√6 sine 2 pi yj. I'm now quoting from a recent paper with Vesa Carnioia and Francis, but in which we decided to change the model. So this is not exactly the same model as the one which is usually studied. The yj, y1 up to y2 are still parameters representing independent random variables, but now we have this sine 2 pi yj in here. So this makes the randomness periodic. It doesn't make the physical field, if you will, periodic, anything like that. It makes the random variable periodic. And periodicity has wonderful benefits in mathematics, as we all know. And what about that 1/√6 there? Well, that 1/√6 is there because if you do that, the mean and variance of our field and covariance of the field are unchanged from the previous model, from the usual model. The usual model, just I flick back to it for a moment, I go back to it. The usual model is that it just has yj's in there in the field, and now we have sine 2 pi yj on √6. The field is Gaussian, it is not Gaussian because our yj's are just uniform, but they are as a random field. The mean and variance are exactly the same, and higher moments, of course, are a little bit different, but hardly at all. And we don't know any reason to think that the other model is any better than this one. We think the model is just as good, as far as we know. We've never seen anyone give an argument in favor of the uniform model. And once you take this point of view, well, now we can move on. We need to truncate the number to a finite number of dimensions, to S dimensions, because that's all we can handle is finite number of dimensions. This, of course, introduces an error, but it's something that we can analyze, control. And I don't go into that. We need to handle the X and Y dependence. For X, we use a finite element method. It's another controllable source of error. I don't go into that. For Y, we use, what do you know? We only use kernel interpolation, as before. So now the function to be approximated depends also on X. So X is hidden, and the error is now more complicated because it's L2 in 2 different senses, integrating over first the physical variable and then over, no comma there, and then over the random variable, over the variable representing randomness. But it doesn't change anything in any essential sense. And so now I come quickly to a numerical example which we've done. This one happens to be two-dimensional. It has details of we made a choice of the psi j, which decay so that we get to finite sums. So on, we've chosen some parameters, and that's in this paper, this Numerische Mathematik paper. But the details of it don't matter. But I wanted to show you first that it does work for 10 dimensions, some choice. There's moderate choice of parameters, moderate difficulty. Theta represents the decay in the psi j's, but is moderate. And we get good results. Look, so this is results which go up to 10 to the, well, 5 by 10 to the 4 number of points, perhaps. And the error going down very satisfactorily, the red points, it's the red dots. Up there is the predicted rate of convergence. Look, I show the same results for S equals 100, because now we can handle high dimensionality without any particular costs. This does, of course, tell us that that problem wasn't so hard. I mean, not really so high dimensional, because the results hardly change. But I do want to emphasize that we can actually do this. We can actually go up to 100 points, 100 dimensions, and up to 10,000 points, 50,000 points, no problem. The dashed line is the predicted rate of decay, so clearly we're doing much better than the predicted rate. Is that impossible? It's impossible for the worst case error, but it's not impossible for a particular function. So we think that's okay. The last point, I want to come to this sort of really crucial point, however, that the weights, this was a very costly calculation because the weights were not product weights. You remember, we find the weights. We find the weights by minimizing this upper bound on the worst case error. And on the norm in the end. And if we get the weights, the details here matter not at all. But the thing is, these are not products because of this initial sum. So these weights are complicated, they're not products, and they are expensive. So we have a rigorous error bound. Everything is beautiful mathematically, but the constant, and the constant is independent of dimension, but the cost is high. The cost is high. Instead of what we had before, now we've got, instead of this terms, the kernel evaluation is hard. The kernel is now more expensive. So we get S squared, alpha squared in here, and we have a higher offline cost as well. So it doesn't make it infeasible. I mean, we don't have exponential growth in the dimension, but it becomes too expensive to be probably useful. And so we asked ourselves more recently, can we get good results with product weights? And because our theory didn't give us product weights directly, but we did have an upper bound anyhow. We've discovered that you can get good results with product weights as long as we give up seeking results independent of S. And I'm quoting now from a paper with Vesa, Carnoia, Francis, and myself, which is incomplete, perhaps drastically incomplete. But we do know that if we choose the weights this way down below, which is a product, and again, the details don't matter, but with some e to j's chosen to maximize the constant in front of the end of the minus 0.85, then we can get essentially the same results. The green are now our new results, the red are the old results. So the new ones are very cheap and efficient. And indeed, we call them serendipity weights. Weights were happily discovered by accident, because we first of all did discover them by accident. And indeed, we discovered that they can sometimes work much, much better than the ones for which we have this beautiful theory. So this was another example. It's a somewhat harder problem, but nevertheless, we can still do beautifully with it. So we tend to think that there is great promise in this as a method, as well as a sort of beautiful mathematics that underlies it. It has both qualities. And if I come now to summarize, the approximation, we're using approximation by kernel interpolation, using lattice points. Our kernel is the reproducing kernel of a specific reproducing Hilbert space H, which is a mixed derivative space of order alpha on 2. We design weights and lattice vector Z, both these things, to control the error, And we finish up with rigor results that, independent of dimension, even if we use our complicated weights, but that method is slow for large S. So in our new project, with this, we insist on product weights. Now the method is fast. We still have a good theory, but the bounds of the weights depend on S. So far, the results are promising, and we don't have too much yet. And sorry about the last sentence. But theoretically, lattice points give only half the optimal rate of convergence. So that brings us question, that's the biggest con of this method. But in practice, they form very well and with a beautiful theory, and often even better than expected. So I just finish us with the two references that I've given, and the third one is not yet written. And so thank you very much for your attention and for staying up so late for some of you. And thank you for that.
Thank you very much for a nice talk. That is the speaker. And please, some questions, comments, and remarks.
Go on.
So I have a question. So you were saying you were talking about the cons of lattice points, and maybe you did mention this at some point. So are there on the torus, are there suggested point sets that maybe would be, or sequences of point sets that would be better than lattice points in certain scenarios, or are those generally not known?
That's a very good question, Ryan. Thank you for the question. I don't know the answer, to tell you the truth. The proof of Byron-Hyde and other, of course, is very clever to specifically use. It's very like the classical arguments on lattice points. It uses those the very simple geometry of lattice points and all that sort of thing. It does seem so. Kammerer and others argue that you can get around this. You can get around this problem by using multiple lattice points in some sense. And in a way, you can sort of see that lattice points are too simple, right? Well, you know, from a number theory point of view, everything that's simple never works, right? So, you know, it has its problems. So, you know, you get around it by combining points from different lattices and so on. But I suppose I don't really understand, and it's a wonderful question. We should pay more attention to it. But at least I have revealed the con, you know, the negative side of we try not to conceal things here.
Okay,
Francis,
thank
do you know the answer?
Please, more questions.
Well,
Oh, sorry.
Hello, Ian. Can I ask a question?
Yoshihito, hello.
Hello. I have a question on the product weight result that you said you did with Vesa and Francis. Which part of the bound depends on S or dimension?
Well, the constant. I mean, well, of course, which part of it? So the constant in front of the power of n.
But if you allow the constant dimension dependence on the constant, why can't you just, if weight is every weight is 1, then don't you still have, because you don't have to care about the solvability is what you're saying, it seems. And if you don't have to care about the solvability, then
yes. Well, you know, in practice, of course, one is always doing calculations with some fixed, you know, in a practical sense, you're doing it with a fixed number of dimensions, you know, as you're wanting to do it with 100 dimensions. In that, I wrote down, perhaps I could go back to it if you wish, that the expression for the weights we use, that they involve parameters eta, j. You know, that this is necessary to, and you choose them varying depending on your problem. You're not trying to choose them independent of dimension. So that means error bound in principle depends on dimension, but it doesn't mean that your error doesn't mean that you can't handle any dimension. It just means we don't have a result that has this it's a beautiful property, right? To have an error-bound independent of dimension. But
Mhm.
it comes at a cost of the kernel the problem, right? Because just to emphasize again, the problem lies in the cost of evaluating each kernel. It gets very complicated for these spot weights things, remembering that in principle you start with a sum over all subsets. So in the product case, that simplifies dramatically. In the spot case, it took a whole paper to work out how to do it. And it remains very complicated. And, you know, truth to tell, most people will not want to do it. They're not going to recalculate they're not going to calculate the kernels in such a complicated way.
Okay, I guess my question is, if you let the weights to be all one or constant, don't you still have the best order, but with...
Yeah, but no, but the order is not the problem. I mean, the problem, if you do that, if you take all the weights to be one, you finish up with an enormous constant and a very bad
Yes, yes, but what you're saying is, if you use the product weight, you can get the small constant.
Yeah,
because
we work hard to get small constant.
Okay, but it still depends on S.
Even the choice of the parameters, the eters, will depend on S.
Okay.
But we don't. I mean, we haven't run across. We don't yet know if there are real limitations. So in our paper with you, I mean, the one we've done, we went as high as 100 dimensions with spot weights, so-called, and 50,000 points. I don't know, the sky's the limit for what you can do with these product weights. Well, we don't know yet, but anyhow.
Okay. Thank you.
Please, more questions or comments?
Can I just respond slightly as well? Just respond to the question to Yoshihito. In our paper before, we were working with upper bounds, right? So, and upper bounds can actually be quite a lot larger than the actual quantity. And so the optimization work with VESA is to actually numerically look for something which actually even behave potentially better than the upper bound, which was theoretically good. So in the end, the numerical result might not have any theoretical proof because our numerical bound is better than the theoretical bound. We are sort of guaranteed by the theoretical result as well. Does that make sense?
The bound, can I just respond to that, Francis, that we have a theoretical bound. We didn't have, it's not sort of a priori. I mean, we have a rigorous bound that has a constant depending on S and on the weights and all those things, right? We minimize, we may not use a general principle, we may use a numerical principle to minimize that constant, but it still gives us a rigorous bound.
Oh, so you get a better rate, is what you mean?
Yeah. No, we're not changing the rate with respect to n. We don't change the rate with respect to n.
Okay, but you get the smaller constant.
The smaller constant, yeah.
Okay.
And but my only point in response to Francis that the result is still rigorous. It wasn't just sort of a priori, and you know, it's for a particular problem and for. I think this work's still in progress, so we haven't yet worked out exactly how to describe it.
Oh, thank you. Please, more questions, comments?
I've been curious since near the beginning of the talk. If you have an answer for it, what is polynomial chaos?
It's a very strange name. I mean, I can't sort of see any real justification for it. It's a terrific name because, you know, it's such an exciting thing. It has nothing to do with chaos. It's to do with polynomial approximation.
I thought it's the polynomial approximation in the random variable where the stochastic variables are. That's how I always thought of it. Whether that's how they come up with the name, I don't know. It's not in the spatial sense, it's the polynomial expansion applied in the variables in the probabilistic sense.
Yeah,
That's my
in
interpretation.
the Y's, in my case, in that, if we may say, in the parameter, you can think about them as parameters once once you work it. That's the way we tend to think of them. But yes, and it is very much really, it's in the classical tradition of polynomial approximation on intervals. It's based on I don't, Vino, I've forgotten now, but did he use Legendre polynomial expansion in each variable? And then, of course, you get enormous numbers of variables. Polynomial chaos in a generalized polynomial chaos just simply allows more variables. I mean, the original paper of Kania, Darkus, and Xu talked about the Wiener-ASCII class of polynomial, allowed a very broad class of polynomials in its and of weight functions and so on. How do you choose those weight functions, by the way? Your model's as good as anybody else's, so choose them however you like. I mean, I would choose them so you have the simplest situation. Maybe that means Chebyshev. But it is, polynomial chaos and generalized polynomial chaos are very much in the classical tradition. Or the papers should all be published in the journal Constructive Approximation, for instance. But they
amen to that. Amen to that.
I thought you might agree there. But it's a terrific name, isn't it? Good name is everything.
Yeah.
And I've read Rena's paper and I cannot see why he gave it that name. But, the paper's quite difficult, actually. Maybe he sort of had a different way of looking at it. But nowadays, and so this leads to sparser, by the way, there's generalized polynomial chaos. There's a tremendous amount of work on it, and it's extremely detailed and difficult because once you get, polynomials, not, products, I mean, you're talking about, polynomials in 100 variables, you can't do it. You actually can't do it, but, 50, 25 variables, you can think of doing it, and people do. But then you need to have most of the coefficients to be zero. So sparsity of representation becomes a really key sort of issue. So there's a tremendous amount of work done in many different places. I'm thinking now US National Lab, our friend Francis, who am I thinking about? Oak Ridge National Lab. There's a substantial group who do a lot of work on this. And
Clayton Webster,
yeah. So thank you for that, Francis. And I mean, it's good work, but it's sort of case you're further and further out on a limb which will eventually break. I mean, because you cannot sort of handle a product of 100 polynomials in 100 dimensions. You can't handle trigonometric. You can handle kernels, and says we never see them in that sense, doing things our way. Or trigonometric. By the way, I mentioned this trigonometric polynomial approximation that we use as an upper bound. Particularly, well, it goes back quite a long way, but it has the problem from an implementation point of view. Francis knows more about this than I do, but so why don't we use that approach? It's a trigonometric polynomial approximation. You have to decide that truncation set of the variables that you use, which I think is in practice a major problem. Am I right, Francis?
sorry, say it, and I didn't quite understand.
That your trigonometric polynomial approximation.
Yes.
That requires you to choose the set A sub S.
Yes, well, in fact, in our analysis, we have a particular choice. We choose the hyperbolic cross. And this is because we are working in the particular setting. We have defined our norm this way. So all the indices closer to the origin are the more important ones. So it makes sense to then choose the hyperbolic cross as our index set. It's part of our assumption of the function space, really.
Yeah. And how about implementation? I mean, of course.
Well, so we have a paper on the implementation side, and the cost will depend on the different type of weights we have. So in the case of product weights, definitely much more efficient. If we have more general weights, then there are different structures in there that we need to take into account. So we were using things like fast Fourier transform we need, but we definitely also need fast Hankel transform to handle some other structure in there. So there were some interesting things in there, I would say, but computational cost is definitely expensive for the best result, the most complicated weights that we want for these PDE problems.
Yeah, so the broad issue, I suppose, arising from the question about polynomial chaos, in the end, polynomial chaos, generalized polynomial chaos, give you a polynomial, a classical polynomial approximation in 100 variables. If it's 100, if S is 100. Francis, that approximation we're talking about there is a trigonometric polynomial approximation, and trig polynomials are much easier to handle, to multiply and so on, to handle when they're multiple variables and so on. And which is why we like the periodic model of uncertainty. And our approximation, on the other hand, is not either of those things, because the ultimate approximation is, in fact, piecewise polynomial on small cubes, but with some C0, C1, C2 smoothness.
Okay, thank you.
Thank you. Please, some more questions, comments? I have a small one. If in some case, instead of product weights to consider general weights, is it possible to get much better constant, or it will not make significant difference, just gives more complicated computations?
Well, we did explore. We didn't explore I mean, there's a limit to what you can do, but we explored. So, well, let me just start again. You have the constant. In principle, you can think about the right way of doing it is to choose the constant that minimizes your whole bound. You have both the worst case error and the norm depend on the weights, and so on. You can choose your weights to minimize the product. That's a bit too. We do that in simple cases. It gets a bit hard. So we look for some reasonable compromises on that, and that has led us to spot weights and pod weights, which are a little bit simpler. The most complicated we've considered are spot weights, and beyond that, we run out of adjectives, perhaps, or descriptors for these things. I don't know, what else you can do. I suppose we do know how well you can do with if you take the general weights, I suppose. Do we, Francis? No, but then we got to some over. I don't know. The general weights, they're through to the S terms in the sum. It's hard to handle in any way.
No, we don't ever have such full generality. No. So we always have to have some structure in the weights. In theory, it deals with complete general weights, but the implementation, we can only handle weights of a certain structure.
I understand. Thank you.
And the spot is already very technical.
Spot is already very technical, yeah.
To be able to handle. To be able to handle the it's the construction, the actual practical construction of the kernel is actually the problem.
Yes.
Because our method is based on using specific kernels.
It's because the kernel goes into the formula for the worst case error, which is our search criteria. So we can prove error bounds on the formula for the worst case error that involves the sum, which is exponential, but that doesn't matter. It's all theoretical manipulation. So the theory is perfectly fine for any crazy way to think of. It's valid anyhow. But the implementation requires the evaluation of these worst case errors. Then it needs to have structure so that we can do things recursively.
Yeah, sure. I understand with some generalized, it's not possible to do some computations. Actually.
Exactly. We basically need to be able to have some sort of recursion to go from one dimension to the next. And when there's
Yeah.
product weights, the recursion is very easy. Normally it means you just multiply by another factor because it's a product form. But if it's more general, then that means the recursion is then very complicated. You have things which depends on, in a way, on the future and the past. And so you have to take all of that into account.
And I just was curious, maybe exist some cases when the general weights could be like much better, or like product weights, like something like this. But I
Not the
understand
computational side, yeah, but the application side, because we want to apply this to the PDE problems, and we want to be able to capture the structure of these PDEs, the regularities. Then we kind of need these more crazy weights to be able to do it.
Sure. Thank you. And please, some more questions or comments? Okay, then let us thank you, speaker, once again. Thank you very much. Very nice talk.